All right, I'm on page 15. Don't have to worry about C and D for the test. Okay, find a relative max, find a relative min, point of inflection. Right. All right, so if I want to go through first derivative tests through quotient rule. Okay. Hopefully pretty straightforward with quotient rule. We still have to do cleanup, but any questions so far? Okay, so I pushed some things together, but we still want to get this looking a little differently so that we can find critical points and populate our slope sign line. What can we do next? Yeah, get a right idea. We're looking at the numerator here. Let's think about factoring. Let's think about GCF. What else is shared besides e to the x? X squared, right? We can divide out x squared and e to the x. That will kind of speed up the process of getting it into a form where we can find critical points. So it looks like they both shared x squared and e to the x. So if I divide out x squared and e to the x, what's left for the first term? 3. If I divide out an x squared e to the x from the second term, right, x cubed divided by x squared is just x. We're on page 15 of the review packet. You guys have that? Yeah, I got to print that out later, but I think you just copy the problem down and look through. Yeah. So we're just starting with a function here, trying to find relative max, relative min. So we're going through the first derivative, then trying to find our critical points. All right, anything that we can do to clean up? Yeah, we can take, once the GCF is out, that's fair game with a denominator. So we can take out one of the e to the x's. All right, so there's my cleaned up f prime. What do we do next? Find what? Yeah, find critical points. So critical points comes from where? Numerator and denominator. So we got to consider both numerator and denominator. Doesn't mean that we're going to find it in both places, but we got to at least consider both locations. Okay, x squared and 3 minus x equal to 0. Okay, those are two separate terms there. Okay, if I try to set e to the x equal to 0, you consider what the natural log graph looks like. What do you think? Oh, okay. So the way we can do this is we can do this algebraically, right? We know that if I want to solve for any variable in the exponent, I can always force it into a natural log problem to bring that exponent down. So I can always do this. And so the x comes down, which is fine, but what's natural log of 0? Undefined, right? If you think about your natural log graph, natural log doesn't live at 0. It only lives to the right of 0. So this is undefined. So there's nothing here. E to the x is never equal to 0. So we only have two critical points, 0 and 3. And we now get to test our slope sine or derivative sine line against our derivative. Okay, there's no restrictions here to the left of 0 because there's no natural log. There's no domain restrictions. We test points on either side here. I can test -1. I can test 1. I can test 4. Into my factor form for my first derivative. So -1 squared is still positive. 3 minus -1 is still positive. E to the -1 is also positive, right? E to the -1 is 1 over E. That's still a positive number. Plug 1 in, positive. 3 minus 1 is also positive. Positive over positive is positive. Four. 4 squared is positive. 3 minus 4. Okay, that's negative. So I get negative up top. E to the 4 is also positive. Negative over positive is negative. Okay, so we do have one relative extrema at 3. If I ask you for interval increasing, you would say first and second interval. If I say actually for interval decreasing, you'll say from 3 to infinity. If I ask you for relative max or relative extrema, you would say relative max. And if I ask you for the full order pair, how would you go about finding that? Original, right? So original is x cubed over e to the x. Moving on to the second derivative function. I'm going to rewrite this f prime. It's a little bit easier to do quotient rule if I can just resolve those parentheses. Moving to the second derivative. All right, so there's my f prime rewritten. Okay, f prime. Morning. All over g squared. Okay, I'm going to just distribute everything through, see if I have any like terms, clean this up a bit. Let's see. Okay, again, GCF from the numerator here, I can take out e to the x and x from every term. I'm going to rearrange this so that I can get it into what I think is factored form or into trinomial with the highest degree. So I'm going to rearrange this, let this be. Oh, I'm sorry, this should be a plus, my bad. So if I distribute this negative through, plus x cubed e to the x. So if I divide out x e to the x from every term, I'm gonna start with this one here. I'm left with x squared. If I divide out x and e to the x, I'm left with just minus 6x. Divide out x and e to the x, I'm just left with plus 6. Okay, e to the x cancels out. So we're just left with, sorry, e to the x. One of the e to the x goes away. There's still an e to the x left. So we're going to set both the numerator and the denominator equal to 0. However, this is not factorable. Got to go through quadratic formula, but on the test, I'll make sure if it's trinomial, I'll give you something factorable. But I'll just jump to what that value is. Two solutions from there, x equals 3 plus or minus root 3. This x equals 0. And e to the x doesn't equal to 0. So we have one critical point here, 2 critical points there, and then none from the denominator. At double prime sign line. All right, I'll test values in each interval here. So I'll test -1. I'll test 1. 3 minus root 3. That means it's less than 3, right? So I'm subtracting root 3. So I know that 3 can live between 3 minus root 3 and 3 plus root 3. And root 3 is around like 1.7. So if I choose 5, I'm safe to the right. Okay, I'll test against my second derivative function. This is negative. 1 plus 6 plus 6, that's positive, negative times positive. My denominator is always positive because e raised to any power, no matter what, it'll always be positive. Even if this e to the raised to the -5, that's still 1 over e to the 5, that's still positive. But first interval, I get negative, so concave down. Plug 1 in, positive. 1 minus 6 is negative, plus 6, that's positive, so everything is positive here. Plug 3 in. 3 is positive, 3 squared, 9, 9 minus 18 as -9 plus 6 is negative. So negative or positive is negative. 5 in. 25 minus 30. -5 plus 6, that's positive. So everything is positive here. Right. By asking for interval of concave down, concave up, you can just pull those intervals from the sign line. Again, don't use these test points anymore. You're just using -infinity, 0, 3 minus root 3, 3 plus root 3, positive infinity. If I ask for a point of inflection, you will say 0, because there's a change in sign. 3 minus root 3, there's a change in sign. 3 plus root 3, change in sign. So you have 3 critical points. Okay. All right, particle motion on page 16. Well, actually, number 2 here. If the function is e to the negative x times exponential of x, then dy dx is equal to when x equals 1. So this is just finding the derivative at a point. But we can extend this out a little more and make it where I asked you for the tangent line equation. So if I find the derivative, that'll give me my slope formula. If I insert the 1 into the function, that'll give me my y value. If I insert the 1 into the derivative, that'll give me my slope. Start off with the derivative. If I want to find the derivative, what rule do we have to involve besides e to the u and natural log? Thank you so much. Appreciate it. Okay, what else do we have to involve besides e to the u natural log? Two terms multiply, so we got to go through what? Product rule, right? E to the negative x becomes e to the negative x times -1, right? E to the u times u prime. G stays, back to f. What's g prime? Natural log of x becomes what? U prime over u, right? So what? 1 over x. Okay, really the only thing I care about from the derivative is get to the slope. So I don't have to worry too much about the cleanup. I can just insert 1 directly into the derivative. All right, natural log of 1 is just 0, so that's nice. I can just wipe this term out. E to the negative 1 over 1, that's just e to the negative 1. E to the negative 1 is just 1 over e. My original function, my original order pair can found by evaluating the function at 1. Again, I have natural log of 1 showing up. That's just 0. Anything times 0 is 0. Okay, so I have everything that I need. Here's my order pair. Here's my slope. A point slope form.
The term that's e to the negative 1 and then out in 1, does that, how do you know that simplifies like to 1 versus negative? Like the negative exponent?
Oh, you mean just this term alone? This one here? Right, so yes, this is negative 1 over e times natural log of 1, but natural log of 1 is equal to 0 by itself. So that just wipes out that whole thing. Okay, good. Any other questions here with 2? Right. Page 16. Particle motion here. Given the position function. I'll put this on a separate sheet as well. Writing expression for velocity, so we can find the derivative. Acceleration, find the second derivative. Okay, thank you. All right, so if I want to find my velocity function, I can just go directly into my derivative rule. E to the u has its own rule. AT is just power rule. Coefficient stays. E to the u becomes e to the u times u prime. 8t becomes just 8. Do some cleanup here. The 3 in the numerator and denominator will go away. Oh, this 3 right here. So we have the rule for e to the u. All right, part B, we want to get to our acceleration function. So take another derivative down. Right, 4 stays. E to the u becomes e to the u times u prime. Now the a just goes away to 0. Okay, when is particle at rest? How do we move forward there? Yeah, velocity go to 0. Yeah. Gonna just move the e onto the left side. It doesn't matter here. Okay, so I want to solve for t, but first I want to get that 4 out of the way, divide both sides by 4. All right, I want to solve for t, but t is stuck in the exponent location, so we know if I can get it into a natural log expression that 3t can come down. I'm much easier time working with an exponent if that exponent can come down. Take natural log of both sides. That exponent is now free to move. 3t can come down in front. Natural log of e becomes 1. That goes away. 3t equals natural log of 2. Solve for t. Either form is fine. You can either divide by 3 or push it out in front, call it 1/3. Okay, t should be easy. Find velocity when t equals 3. Just insert 3 into the velocity function and find the velocity.
Keep trying these.
Hmm?
Should I keep trying these, but I finish the test?
Uh, yeah, I mean, you have time right now. All right, part E, find acceleration. Just insert 3 into the acceleration function. Okay, at t equals 3 is the velocity of the particle increasing or decreasing. How do we interpret this and how do we, what steps do we take? Right, is this really talking about velocity? That's right. Good, good. Yeah, so the velocity, I know we see the word velocity, but it's not really talking about velocity. The word increase, decrease is really, it's talking about the rate of change of velocity, which is really, it's just acceleration. So we just look at acceleration. So we have a of 3 already, right? A of 3 is equal to 12e to the 9, and that's greater than 0. That's all we need to make our conclusion. Positive acceleration means velocity is increasing. Okay, at t equals 3 is the speed increasing or decreasing? Sorry, say again?
So only check both of them.
That's right, we check both sides. And conveniently, we have both d and e to help us out. 4e to the 9th, that's a pretty large value. That's like 3 to the 9th power. It's a much greater, that minus a is not going to do anything to it, it's still positive. So you got a positive velocity, you got a positive acceleration. They're both the same signs, therefore speed is increasing. Right? What if these are both negative? Still increasing, right? But if one is negative and the other is positive, or vice versa, the signs are different, then my speed is decreasing. Right, any questions there? Very good here. All right, number 4. All right, so if I want to find the derivative of this equation, let's list out possible steps we have to take. What do you see here? What's involved in our process? Implicit, yeah, you see the y's all over the place. You got to collect your dy dx's there. What else is involved? What else do you see? Anything else stand out about this equation?
Just put the LN.
Right. So this is actually something that we can do before the derivative, right? That natural log of xy. Prefer not to do the derivative with this expression, right? If I can split that up, and I can, because I can expand log properties. That will help me a great deal. So I don't have to work in a much more complicated derivative rule. Now we can just jump into our derivative rule, right? u prime over u for my natural logs and power rule for my variables. Or for my right side. Okay, natural log of y becomes u prime over u, right? 1 over what? Times. Yeah, I see y in my expression, so implicit, I gotta collect all my dy dx's there. Right, natural log of x. Y squared. Yeah, 2y is power rule. We're asking for y's derivative. We need that dy dx. Okay, x cubed. Minus e becomes now e is around 2.7 as a constant, right? What happens to a constant? What's the derivative of constant? 0. Right. E, I know e is a symbol, but it's still a number, like pi, just some decimal value. Right? Goes 0. All right, let's collect our dy dx's. Drag the non-dy dx's over to the right side. Factor out dy dx. Divide my parentheses over. And I do want us to clean this up, so let's practice doing that. Think of the numerator and denominator as separate fractions that we can merge together if we have common denominators. So I'm going to force a 1 in the denominator in each fraction. I'm going to handle these separately. So here, for my upper fraction, I see my common denominator will be x. Balance each fraction. My first denominator is missing an x, so I need to multiply the top by the x. Second fraction, my denominator is already matching, so I can just keep that minus 1. All right, my bottom set here, common denominator is just y. No balancing needed. I can keep that 1. Second fraction, it's missing a y, so I need to balance the numerator with a y as well. Okay, so this cleans up here. Now that I have common denominators, I can at least get it down to a complex fraction. All right, so fraction divided by a fraction, but fraction divided by a fraction is the same thing as fraction multiplied by the what? Reciprocal, right? So that allows us to get something cleaned up. We can get this denominator fraction to flip up to the top. Now we can just put it all together. Just distribute the y through, distribute the x through, and we have a much cleaner presentation of our derivative. That's my slope formula. I want to find the slope at any point on this original graph. I just need a full order pair X and Y, and that'll give me a number, and that number is gonna be the slope of that graph. All right, let me create a quick problem here, see if we can do this one. Call this number 5. Okay, 3x minus 1 raised to the square root of x. Do we have a derivative rule that can handle this setup, this format? Yeah, it looks like maybe chain rule, but here's the issue. This is a variable base raised to a variable exponent. Any idea what we do if we see that situation? Not power rule. It's not exponential rule. It's not a to the u. So the issue is that we don't have a rule that can handle this. But it's just something that we can do to force this to look a little differently. Yeah, good. So the whole idea is that I don't want this exponent here because I don't have a rule that can handle it. But if I can somehow find a new location for this exponent, then I can maybe have some more options available. And I want to find a way to bring that exponent down, but I can't bring that exponent down unless it's part of a log or natural log problem. So I'll just write it as x to the 1/2, just to get it ready. Take the natural log of both sides. So now that I have natural log of a to the u, that exponent can be free to move down. There's not any derivative process here, but it does allow some options opening up for us. Right, before we didn't have a rule available, and now we have rules available, right? Now this feels much more manageable, right? What can we do on the right side here? Product rule, and left side is a little bit of what? A little bit of implicit. Okay. Natural log of y's derivative is dy dx. Okay, product rule on the right side. F prime, power rule, times g, back to F, g prime, e prime over u. Okay, one more major thing to do. What's that? Yeah, get that dy dx by itself. So we move the y over to the right side. Do some cleanup. Then let's just force this down to be just one fraction here. All right, one more thing. We don't want that y there. That's just a temporary variable. What can we do with that y? Replace with original function, right? Isn't that what y is equal to? No need to find common denominator, just try to do some cleanup within each individual space. Your log differentiation, this is what this process is called, log differentiation. Your derivative will just look a little messy, and that's fine. Okay, we've hit the majority of the types of problems that you're going to see on the test. We did some curve sketching, we did some particle motion. Maybe we skipped over some of the problems that you guys saw on the quiz, but the quiz looked pretty good. Implicit we hit, log differentiation we hit, tangent line equation we hit. We didn't quite do inverse at a point, but we can practice that in class today as well. All right, any questions? All right, I'll be available fifth period lunch and after school, and we'll do a help session tomorrow morning as well.
Yes, we just check.
I'm not going to seriously grade everything yet. Thanks.
No problem.
Yeah, it's on the website. It's at the very top of my unit page. You'll see a packet there. Yeah, I'll try to print out some today too, but yeah, you can find the website.
Almost like the physics one,
Mhm.
like the AP physics one.
I think there's some.
Because I mean, actually, I had to do velocity versus time graphs and acceleration versus time graphs. Which
Yeah.
might be helpful.
There's a little bit of connection, but we really only spend like, we don't spend a whole lot of time in it here. We just do derivative and that's it.
Also already learned vectors, so is that gonna help with the problem?
Vectors, you see it in BC calculus, but not.
Christian, we do vector.
Oh, that's right, that's right. We do.
Like summings and that and stuff.
Yeah, we just put everything up into components.
Like how you
Yeah, no, it's just like, our, literally, the inside of our restaurant is in Mercedes. I feel like I'm like so much, yes, it's smaller, like, it's my brain. Like, this, like,